Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 31st lecture. In this lecture, we will be discussing some basic concepts related to design for testability or DFT. Before proceeding further, let us recap what we had discussed while taking an overview of testing. So, we had discussed that there are some design tasks which are carried out during the design phase, that is while we are transforming our design or implementing our design and taking it from RTL to the final layout. During the design step or during the design process, we carry out certain design tasks which are basically targeted for testing, and these design tasks make testing more cost effective and efficient. So, these design tasks which are targeted for testing, these are grouped together and called as design for test. Now, before proceeding further, let's also recap that how testing is done. So, the most popular method of doing testing is using automatic test equipment. So, in this testing method, what we do is that we take the fabricated die and apply test patterns on those fabricated dies with the help of automatic test equipment and see the actual responses that are obtained for the fabricated die. If the actual responses match the expected responses, then we say that the given die has passed the test, and this die will be allowed to go to the next go to the customer or go to the packaging and so on. While if there is a mismatch between the actual responses and the expected response, then we say that the testing has failed, and then we reject that die, and that die do not go to the customer or is not processed further, right. So, this is how the testing of or manufacturing test is done, right. Now, for this manufacturing test to be more testing process to be more efficient, we need to make some changes in our design. We need to insert some logic and test structures in our circuit, so that our circuit becomes more testable, right. So, this process of making changes in our design is related to or are the design task which make these changes to our design. Those are known as design for test or DFT task, right. And the other important step that is carried out during the design process is to extract test patterns which need to be applied to the fabricated die and also the expected responses, right. So, these are some of the design tasks which are targeted for testing, and in this lecture and in next 3 lectures, we will be looking at these design for test or these tasks which are targeted for testing or DFT task, right. Specifically, in this lecture, we will be first looking at some basic concepts related to DFT. Now, for carrying out testing, we use a testing method which is known as structural testing. So, let us first understand what is structural testing. Suppose we have a circuit which implements a Boolean function with n inputs. Suppose there is a circuit and we have n inputs, n Boolean variables, n inputs are there, and it is producing some output, right. Now, if we want to test this circuit, how can we do? One of the ways can be that we apply test patterns. What are the possible values that can come at the inputs of this circuit, right. So, we apply those test patterns, for example, 0, 0, 0, 0, 1 and so on. So, if there are n variables, then 2 to the power n different combinations are possible, and then for each combination we check what is the value y produced by this circuit, and compare whether it is as per expectation or not, right. So, this method is known as functional testing, right, and this is the same and this kind of thing we have already looked when we discussed functional verification of our RTL, right. Now, this technique will become infeasible if say we have very large number of Boolean variables. For example, say if the n is 50, right. If n is 50, then the number of test pattern that we need to apply will be 2 to the power 50, and then we in a limit, and to apply so many test pattern, it will need a lot of time, and therefore the cost of testing will increase, right. So, the cost of testing depends on how much time we spend for a given die on the ATE equipment or automatic test equipment. If there are large number of test patterns that we need to apply, then we need to keep that a given die for a longer duration on the ATE, and therefore the test time will increase, and therefore the cost of testing will also increase. And therefore, when n is large, then we cannot afford to do functional testing. So, in that case, what we do is that we follow another testing paradigm, which is known as structural testing. Now, what do we do in structural testing? In structural testing, we test the components of that implements a logic function. So, we go deeper into this circuit C, and there will be say a logic gates inside this, which will be used to realize this function, this Boolean function. So, we will be actually testing these components which are there inside our circuit individually, right. So, test the components that implement a logic function rather than testing the input output functionality, right. So, that if this testing paradigm is known as structural testing. In structural testing, we are not testing the output behavior of our circuit. Rather, we test each individual components in our circuit, and if the individual components are found to be good, then we say that our circuit is passing the manufacturing test. Okay. So, the paradigm of structural testing is widely employed in manufacturing test, in VLS, in the semiconductor industry. And why it is very popular? The reason is that it reduces the number of test patterns that is required to ensure or perform testing efficiently is comparatively much lesser for structural testing than with the functional testing. Therefore, the structural testing paradigm is widely employed in the semiconductor industry. So, now let us look into the functional differences between functional testing and structural testing in more detail. Suppose we are given this circuit which is shown here. So, in this circuit there are say 4 or 5 NAND gates, right, G1, G2, G3, G4, G5, right, 5 NAND gates, and there are X1 to X16, there are 16 input ports, right. Now, if we want to do functional testing of this circuit, then how many test vector will be required? So, since there are 16 input ports, we will require 2 to the power 16 or 65,536 input combinations, right. So, this many test vectors will be required if we do functional testing or the input output, if we are trying to compare the input output behavior of the expected response and the circuit which is manufactured, right. Now, yes, if we do structural testing, how many test patterns will be needed, right. Now, to test one of the gates, say suppose we want to test G1, right, G1 gate. This is a NAND gate. So, this has got 4 inputs, right. Now, if we want to just test this NAND gate, how many test vectors will be requiring. In this case, since the number of inputs is 4 for the NAND gate, we will need only 2 to the power 4 or 16 input combinations, right. And since there are 5 NAND gates, will require 16 into 5, that is 80 test patterns to test individual these components, right. So, we have come down from 65,000 or around 65,000 to 80. There is a drastic reduction in the number of test patterns required, right. So, in that sense, structural testing is very efficient. It requires very less number of test patterns, but there are certain assumptions involved here. And what are those assumptions? So, if for carrying out structural testing, we need to observe the output pins of all the components, right. So, if we want to we want to test whether G1 is functioning correctly, or it is giving the NAND gate G1 is correct, or it has been manufactured correctly, then we need to observe the value of this its output, right. So, when we apply say a test pattern x1 at x1, x2, x3, x4 as say 1 1 1, we expect that this G1 gate will produce an output of 0, since it is a NAND gate, right. But do we have a way to see this signal or observe this signal? The answer is no. Why? Because when we apply test pattern to our circuit, we have access to only the input ports and the output ports, right. So, only these points are accessible for the to the test equipment, and this point is accessible. The internal nodes or internal nets of the design or the circuit are not accessible to the automatic test equipment, and therefore, we cannot observe these nets N1, N2, N3 and N4, right. So, assuming this is may not be correct, right. Assuming that we can observe the output pins of all the internal components of our circuit may not be correct, right. Now, we can the other thing is that we have assumed in structural testing is that we can write any value at the input pins of all the components. For example, if we suppose that we are trying to test this G5, then we are saying that we can easily apply a test pattern that is 1 1 1 1 at the inputs of the gate G5, right. But this the nets N1, N2, N3, N4, those are internal nets. Those are not directly accessible to the AT test equipment, right. And therefore, we can the assumption that we can write any value at the internal nodes of the circuit, that is not correct, right. And the third assumption that we have made in structural testing is that there can be problem in the integration of the components which we are not considering. For example, this net was broken, right. The individually this G1 gate this component and G2, G3, G4, G5, all these components may be working perfectly fine, but the interconnection between them may not be working properly, and that also we need to test during manufacturing test. So, these are some of the assumptions that we made while deriving that only 16 patterns are required for structural testing. Okay. So, though the structural testing requires very less number of or significantly less number of test patterns compared to functional testing, but it makes assumptions about accessing internal nets and also the integration of the components, right. So, now DFT techniques or the design tasks that we carried out which are targeted for testing, those make those tasks make changes in our design, those tasks make changes in our design such that these assumptions, these three assumptions becomes more or less valid for for our circuit, right. So, the goal of DFT techniques is to make structural testing more effective by ensuring that these assumptions hold, right. We can easily control the internal signals, easily observe the internal signals, and also verify the interconnections between the components, right. So, now how these DFT techniques ensure that these assumptions are valid, we will see in the today's lecture and in the subsequent lectures. Now, the manufacturing test is done with the help of fault models, right. So, we design test methods or test patterns or extract test patterns by assuming a fault model for our circuit. Now, what are these fault models? So, fault models represent a defect using a logical or electrical model, right. So, let us take an example. Suppose we had an AND gate, we had two inputs A and B, and it was producing an output Z. Now, for this AND gate, we made a layout, and with this A line was running, B line was running, and also a ground line was running, right. Now, because of the random variation in the processes, a conducting test particle came and it shorted the line B and ground, right. So, this is a defect, this is an example of defect. Now, our circuit has got a defect, right, and it is a fatal defect, it may be a fatal defect because it is shorting the line B and the ground, right. So, this defect can be represented using logical or electrical model, right. That is what the fault model is. So, how can we represent this defect using a logical or electrical model? We can represent it using, say, making this ground, say B line stuck to ground line, right. So, we say that B is taking a constant value of 0, right, because it is shorted to ground. So, this is a representation of a defect, and this is known as a fault. We have said that we are representing the defect. Defect is a physical phenomenon, right. There is a physical phenomenon which is observed on the layout, right, or on the die, right, and we are representing that defect in a circuit model using a fault model, right. So, this is what a fault model is. Now, why do we use a fault model? What is the purpose of using the fault model? So, fault models allows us to analyze the impact of defect using logic or circuit analysis techniques. For example, if we said that we have modeled the defect of the short circuiting line B and ground using this circuit, using this fault, then we can analyze the impact of this fault by saying that this B line is equal to 0, and since this is connected to an AND gate, the output Z will also become 0, and then this fault will propagate and so on. So, we can apply the circuit analysis techniques once we abstract out the impact of defect to our circuit. We represent the defect in the circuit and then use the circuit analysis techniques to carry out further design task, right. So, and it allows deriving test patterns algorithmically for detecting a given fault, right. Now, once we have got represented the defect in the form of a circuit, now we can use in our design task, for example, extracting the test pattern, right. Now, suppose this B line was grounded, right, B line was grounded or B was stuck to 0, right. Now, if we apply a test pattern, say A is equal to 1 and B is equal to 1, for a good circuit we expect that Z is equal to 1, right. But if this line B was stuck to 0, Z will produce a value or the value that will be produced at Z will be 0, right. So, we can say that A is equal to 1, B is equal to 1 is a test pattern, right. Now, once we model the defect in a circuit, we can apply various algorithms to extract test patterns, And how to extract these test patterns and what is the algorithm, we will be seeing that in the subsequent lectures. And so, we can also use the fault model to assess the quality of testing, right, meaning that if we say that defect is causing this fault and the manifestation of defect is some form of logical defect, right. Now, whether our test patterns are catching those conditions or circuit conditions or not, we can measure it using circuit analysis techniques. And based on that, we can say that whether our quality of testing is good or not. So, fault model allows us to have a quantitative assessment of testing or effectiveness of testing, right. If we are able to cover most of the fault in our design, in our testing, we say that the testing is good. If many faults are being not detected, meaning many possible faults for a given fault model, if we are not able to catch them during testing, then we say that our testing method is not effective, right. And these kind of quantitative assessment we can make after we have modeled the defect as a fault. So, the fault model basically transforms the problem of defect detection to the problem of fault detection, right. Now, there are various kinds of fault models that we use for integrated circuit. Now, let us look into one of the most popular fault model, and that is known as stuck at fault model. Now, what is a stuck at fault model? Stuck at fault model assumes that defect causes the signal to be permanently stuck at a constant logic, right. It transforms the defect to logical fault model, and there are two types of stuck at faults. The first one is known as stuck at logic 0 or stuck at 0, and we use the short form SA0 to say that a given signal is stuck at logic 0, right. And similarly, there is another type of stuck at fault which is known as stuck at logic 1 fault, and in this case the given signal is stuck at 1 and we abbreviate it as SA1 fault, right. So, now let us take an example. Suppose we are given this NAND gate, right. It has got 4 inputs A, B, C, D, right. Now, if there is a stuck at fault or stuck at 0 fault at the pin A, right. If the pin A is say stuck at is shorted to the ground line, right. Then we model it as a stuck at 0 fault, or we say that A is stuck at 0 and we write stuck at 0. Similarly, if the A line was shorted with VDD or power supply line, in that case we will say that A is stuck at 1 and in short form we say that SA1 is there at the line A, right. Now, there is another fault model which is known as single stuck at fault model, which is very popular. Now, what is single stuck at fault model? In single stuck at fault model, we assume that there is only one fault active at a time in our circuit, right. And why do we use single stuck at fault model? So, we use it because it reduces the complexity of test pattern generation significantly, right. Now, given our circuit, say a circuit which is consisting of say millions of gates and millions of nets, is it fair to assume that only one fault is active at a time, right. So, on the surface it seems that it is very unfair, right, because if there are say millions of nets in our design and the fabrication process is a kind of or getting defects during fabrication is a random event, then we can have multiple faults simultaneously on our chip, right. So, the assuming that only single fault is active at a time in our circuit, may not be correct, right? But still we use single stuck at fault model. Why? So the reason is that the test patterns or the set of test patterns that we derive using the assumption of single stuck at fault model, those are able to capture 99 or those are able to cover 99% of the multiple stuck at fault in our circuit if there are multiple outputs in our circuit and the logic structure is fairly complex, which is there in our industrial designs. In those cases, the test patterns that are derived using single stuck at fault model assumption, those are able to cover 99% of the multiple stuck at fault also. Therefore, the quality of the testing does not suffer by making this assumption, right? And therefore, the single stuck at fault model is widely used in the industry because it reduces the complexity of test pattern generation without sacrificing the quality of testing. Now, let us understand that where can faults occur in our circuit and what are fault sites. So, the point where a fault can exist or we assume it to exist, that is known as fault site. Now, how do we emulate a stuck at fault in a circuit? So, when if we have a circuit and we want to emulate, suppose we have say a NAND gate as an inverter driving another inverter, right. Now, if we say that the input input of this inverter I2, let us name it I1 and I2, we say that this one was stuck at say 0. Now, when we want to do a circuit simulation or fault simulation for the case when there is a fault occurring in our circuit, right, how do we emulate that conditions, right. So, we emulate it by disconnecting the corresponding source, meaning that we disconnect the line between I1 and I2, we disconnect it, right, and tie it to the constant logic, right. We connect it, we say that this input is being held to constant logic 0, right. In this case, it was stuck at 0, therefore, we tied it to 0. If it was stuck at 1, we will tie it to 1, right. Now, for a given net, how many fault sites can be there, right. Now, if the net is a fan out free net, meaning that for this net the number of pins in the fan out is 1, right. So, if the fan out is 1 or it is this kind of nets are known as fan out free nets, in that case the number of fault site is 1, right. If this one is say stuck at 0, if the input is stuck at 0, we or say this Z is in or the Z out pin is stuck at 0, both are considered as the same, right. And therefore, the number of fan out the fault site for a fan out free net will be 1. But what about the nets which have fan out more than 1? For example, this net N2, right. In this case, how many fault sites will be there, right. Now, in this case, suppose there is a fault at this point at the output of G1, suppose this one was stuck to 1, right. If this one was stuck to 1, then it means that all the driven pins will get a value of 1, right. So, in this case, this stuck at 1 at the pin Z of G1 will lead to fault in all the driven pins, right, all in the fan out. However, suppose there is a fault at this pin, right, this pin only, the input, this pin that is the input pin A of G2. Suppose this was stuck to 1, right. Then in this case, even though the G2 is stuck to 1, the other gates, for example, G3 and G4, those may be working fine, right. So, we have to differentiate whether this one the input of G2 is is stuck to 1, or input of G3 is stuck to 1, or input of G4 is stuck to 1, right. So, there can be there can be 4 different ways in which fault can happen, right. It can happen at this point, it can happen at this point, 3 in the fan out, plus it can happen in the output of G1, right. So, if there are n fan outs, so in this case there are 3 fan outs, then how many fault sites will be there? It will be n plus 1, right. In this case there were 4 fault sites, 1 fault site, second, third and fourth, right. So, depending on how many fan outs are there for a given net, the number of fault site will be either 1 or n plus 1, right. Now, let us take an example of a circuit and then understand that where the faults can occur and what kind of how many possible faults are there under the assumption of single stuck-at fault model. Okay. Now, consider this circuit. Suppose this circuit was given to us, right, and we are asked the question that how many single stuck-at fault are possible in this circuit, right. Now, to find out the number of possible stuck-at fault in the circuit, we need to first find out that how many fault sites are there for this circuit, right. So, in this case of course, there will be the fault sites are the input ports, these are the fault sites, right. And then if we look into the net A, this one, there is only one fault site, right, because it has got a fan out of 1, right. And for the net which is connected to B, how many fault sites are there? One at this input and another at this one, right. And of course, the fault can also be at B. Now, for C, how many fault sites is there? Only one, right, because there is it has got the fan out of 1, right. Now, for F4 there is only one fault site, for F5 there is one fault site, and for Z there is one fault site, right. So, how many total fault sites are there? One is A, B, F1, F2, F3, 1, 2, 3, 4, 5, 6, 7, 8, 9, right. Now, on each fault site we can have 2 types of fault, stuck at 0 and stuck at 1. So, total how many faults are possible? 9 into 2, that is 18 faults are possible, 18 single stuck at faults are possible for this circuit. Now, let us look at how we can detect a fault in our circuit. So, we detect faults in our circuit using test vectors. Now, what are test vectors? So, test vectors are any input pattern or a sequence of input pattern that produces a different response for a faulty circuit and a fault free circuit. For example, let us take that this is our given circuit and these are the inputs, right. Now, we can apply a pattern, a sequence of zeros and ones at the input such that the output that this circuit produces for a faulty circuit and a fault free circuit are different, meaning that say for faulty circuit it is producing 0 and for a fault free circuit if it is producing 1, then the input pattern that we have applied to our circuit, that is known as the test vector or test pattern, right. Now, for a given circuit of a element, for example, say we have a NAND gate, right. If we want to exhaustively test the functionality of this NAND gate, will require 2 to the power n number of input combination, where n is the number of inputs. So, in this case, since there are 4 inputs, will require 2 to the power 4 or 16 input combinations, right. But can we derive a set of test vectors which is much less than 16 and are able to capture all the defects in our or faults in our circuit? So, the answer is yes, and for that we take help of the fault models. So, what fault models, or for example, the single stuck at fault model does is that it makes the number of faults that needs to be detected in our circuit as linear in the number of circuit elements, right. So, since the number of faults that we need to need to detect in our circuit, that becomes linear, the number of test patterns that will be required to test our circuit, that also reduces drastically, right. So, let us take an example and understand that how can the assumption of single stuck at fault model help in reducing the number of test vectors. So, let us take a case in which we have say a 4 input NAND gate, and we want to we assume that single stuck at fault model is valid for this case. So, since there are 4 input pins and 1 output pins, and each of them can have a stuck at 0 and stuck at 1 fault. So, number of faults that will be there that needs to be detected for this circuit is 5 into 2, that is 10 faults, right. So, since there are 5 pins in the in this component, and each can have 2 types of faults, stuck at 0 and stuck at 1 will have 2 into 5, that is 10 number of stuck at fault that we needs to be detected. Now, let us derive the test patterns for detecting all these 10 stuck at faults. So, first let us see that if our circuit is fault free and this is a NAND gate, then since there are 4 inputs, we have 2 to the power 4 or 16 input combinations, right. And for the case when all the inputs are 1, we have a value 0, and in other cases we have the output value as 1, right. Now, let us assume that that in our circuit stuck at 0 fault occurs at this point, this is stuck at 0, this is grounded. So, A becomes 0. Now, if A becomes 0, then what will be the value of Z? So, in that case, for all input combination we will have the output as 1, right. And then from this truth table we can derive that what is the test pattern. So, remember that, or what is the test vector. So, remember that test vector is the input combination that produces different output for a faulty circuit and a fault free circuit. So, we see that only for the test pattern 1 1 1 1 1 sorry 1 1 1 1, we have the value produced at the output Z is 0 for a fault free circuit and 1 for a faulty circuit, and therefore 1 1 1 1 is a test vector to detect a stuck at 0 fault at the pin A, right. Similarly, to detect stuck at 0 fault at pin B, C and D, we can use the same test pattern, right, that is 1 1 1 1, right. Now, for the stuck at 0 at the output 0, sorry output Z, what will be the test pattern? In this case, for any input combination other than 1 1 1 1, right, the output will for a faulty circuit is 0 and the output for a fault free circuit is 1, right. So, all these are valid test pattern except this one, right. Similarly, we can derive the test pattern for the case when A is stuck to 1, B is stuck to 1, C is stuck to 1, D is stuck to 1 and Z stuck to 1, right. So, these are the patterns, right. For example, if we take A stuck to 1, right, if A is stuck to 1, then for the test vector 0 1 1 1 1, right, the output produced by a good circuit will be 1, right, the output produced by the good circuit will be 1, but output produced by the bad circuit or faulty circuit will be 0 because A is held to 1, right. So, a valid test pattern to detect a stuck at 1 fault at A is 0 1 1 1, right. So, we see that we see that the number of test or the test vectors that can test all the stuck at fault in our circuit is 1 1 1 1, 0 1 1 1, 1 0 1 1 and 1 0 1 1 0 1 and 1 1 1 0, right. So, these 5 test vectors can cover all the stuck at fault in our circuit, right. So, instead of 2 to the power 4, that is 16 input combination, we need to apply only 5 combination, right. So, since there were 5 4 input pins, we required 5 test vectors to detect all the stuck at fault. So, in general, if there are say n inputs for a NAND gate, then we will require n plus 1 number of test vector to cover all the single stuck at faults in the NAND gate, right. Now, this is the story about one component only, right. Now, we want to test this NAND gate when it is lying inside our circuit, right. Now, when this NAND gate is sitting inside our circuit, we need to apply the test pattern to it, right. Now, if this NAND gate was directly connected to the input port, right, the AT equipment could have directly applied the test patterns at the input pins, right. For example, suppose the test vector we needed to apply was 1 1 1 1, right, and this NAND gate was directly connected to the input port, then the AT could have directly applied 1 1 1 1 to this NAND gate, right, and testing would have been easy, right, or the application of test vector would have been easy, right. But as we move this NAND gate deeper into our logic, for example, here we have shown that this is the NAND gate, and in its fan in there is a complicated logic structure, a Boolean function which is implemented using logic gate. There can be several levels of logic gates in its fan in, right. Now, in this case, if we want to apply say 1 1 1 1 1 test vectors, right, to at the input pins, we need to find out what would be the right combination of values such that we get the right the correct value at the input pins of this NAND gate, right. So, as the gate moves deeper inside our circuit, the application of the required test vector on that component becomes more and more difficult, because intervening logic structure will not be may not allow to pass some test pattern directly to the input of the logic input to the component we want to test, right. So, if the NAND gate was lying too deep in a circuit, it is difficult to apply the required test pattern at the inputs, and this ability to set any desired value 0 or 1 on the internal signals of a circuit by applying an appropriate test vector to the primary input, this is known as the controllability, right. So, the ability that we apply that we can apply a test vector easily at the input pins of our component or at any given internal signal in our circuit, the ability to apply the arbitrarily 0 or 1 at a given internal signal in our circuit from the input ports, that ability of a circuit is known as controllability. For example, if this NAND gate was sitting very close to the input port, the controllability would have been higher. As it goes deeper into the logic structure, the controllability may become inferior, right. Similarly, the output of the NAND gate will be difficult to observe at any primary output if the NAND gate is lying too deep in the logic structure. So, for example, we want to see once we apply the test pattern say 1 1 1 1, the correct fault free NAND gate will produce a 0, right. But if this was a faulty NAND gate, it might be producing a 1, right. Now, we want to observe this 1 on some of the output port, because that is only accessible to the automatic test equipment, right. So, but if this component was lying much deeper in our logic, then observing this one or the faulty behavior at the output would have been more difficult. So, this is this ability to examine any internal signal by propagating its value to a primary output by applying test pattern at the input is known as the observability, right. For example, if this NAND gate was sitting very close to the output port, its observability would have been higher, but if it is away from the output port, its observability is inferior. Now, this is the problem of observability and controllability becomes more complicated for sequential circuit, right. Now, if there is a sequential circuit, we can model it as an FSM, right. So, we can say that these are the state elements, these flip flops are the state elements, and these are driving the combination, and the combinational logic cone is being driven by these state elements, right. And now, when we want to apply test patterns to the test pattern to our combinational circuit elements or components, right, we must produce correct set of values at the output of the state elements, right. So, the difficulty in applying correct values at the output of the state elements, that is the problem of controllability. Now, setting a particular value at any pin in a sequential circuit is more difficult than a combinational circuit. Why? Because several cycles may be required to write a particular value, right, and a state traversal can be required, and the number of and finding such a test sequence is time consuming by sequential ATPG tool. So, let me explain what this means, right. So, suppose we wanted to apply a test pattern 1 1 1 1 at this component, this NAND gate, right. Now, these inputs are being driven by the flip flops, right. These are driven by the flip flops or state elements, right. Now, to get these values at the input of the NAND gate, we must have 1 1 1 1 at the output of this flip flops, right. Now, these flip flops can be part of an FSM, and getting this 1 1 1 1 at the output or the state 1 1 1 1 at the for that FSM may not be easy. It may require many cycles to reach that state. For example, suppose these flip flops were part of a counter, right, and the counter starts from 0 0 0 0, right. So, to reach the state 1 1 1 1, it will require 2 to the power 4 or in the range of 16 cycles to reach that state, right. So, that is why we say that if we want to get a value at the output of the state elements, we will require state traversal. In this case, state traversal from 0 0 0, then to 0 0 0 1, and so on up to the state 1 1 1 1, right. And doing state traversal can be exponential in the number of state elements, right. And therefore, reaching the correct state for an FSM that will deliver the required test pattern at the components, it may require the exponential number of clock cycle. It will increase the test time and the cost of testing. Additionally, the finding that the correct sequence of this state traversal, which will give us this test pattern at the combinational circuit element, that will also require high computational or require more difficult or challenging computation. So, it will make finding the test pattern also more difficult, right. And a similar kind of problem occurs when we try to observe the problem of fault or the effect of the fault in a sequential circuit. To observe the value, say 0 or 1 for a combinational circuit at the output, at an output port, we might require again a state traversal, and the number of state traversal will be maybe exponential in the number of state elements, right. So, the controllability and observability of a circuit is very difficult for, or more difficult for, a sequential circuit, and therefore, we need to make some circuit modifications, or we make some changes in our design such that the controllability and observability in a sequential circuit that improves. And how we can, and what changes we can make, and how, and what changes needs to be made in our design, we will be looking that in the subsequent lectures. Now, if you want to go deeper into the topics that we have discussed in this lecture, you can refer to these books. Now, to summarize, in this lecture what we have done is that we had covered, or we have looked into some basic concepts related to DFT. So, we looked into that what is structural testing, or what is structural testing paradigm, and how it differs from functional testing. We looked into fault models, we looked into that what are test patterns, and we also looked into that what is the problem of controllability and observability in a sequential circuit. In the next lecture, we will be looking into a design methodology which is known as scan design methodology, which basically improves the controllability and observability of the signals in a sequential circuit. Thank you very much.